I'll repeat two of previous lecture slide. This is the simplified circuit diagram of LLC, resonant converter. As I said, this is a practical transformer with relatively large leakage inductance and also reasonable magnetizing inductance. Origin of this structure or the values of relatively large leakage inductance and relatively small magnetizing inductance, they are coming from the inherent structure of this transformer. As I said, for the high voltage application, you need many number of winding. It's getting thicker, so there is a, this window. This is very thick, but there is some leakage flux creating the leakage inductance. That is one thing. Another thing is for the home electronics, like this one is what? Planar display, okay, TV, like that. And for that electronics, you need to have very small, low profile power supplies. For that, you need to have planar type transformer. Another one is contact-less power transformer. That case, there is a huge, considerable leakage inductors in between. Okay, both if there is the core, will be better, but there is no core. Without any core, you can still transfer power. Then leakage inductance is very large. Okay, so with those structures, that transformer says this large leakage inductance and relatively small magnetizing inductance compared to the conventional transformer. And this leakage inductance is also located here. Okay, so this is the structure. And one final thing, probably more important than previous things, are LLC converter has very good properties as a DC-to-DC converter. So to have such a nice properties, some people intentionally use this LLC structure. Okay, you will know this later in the later part of this lecture. Okay, in every aspect of the circuit property of the converter, LLC is the best you can achieve. Right? Okay. So this was symbol of practical transformer, and this is the symbol of ideal transformer. As I said, this is not an inductor, not a winding, just the symbol. Okay, it obeys the mathematical definition. We select it. Okay, but this leakage inductance in the second side can be moved just by dividing this leakage inductance in the secondary side by n squared, which is turns ratio. Then we will have this structure. So this inductor, secondary leakage inductance is moved to here, okay? Then we have approximation here, okay? This is the exact. This guy can move out here if these two conditions are satisfied. So those two conditions are this one. Lm is much larger than L leakage in the secondary side. And another assumption here is this magnetizing inductance is much larger than transferred leakage inductance of secondary side. LKS, right? Divided by n squared. Okay? If these conditions are met, then this guy came forward, so it appears here. Then we combine these two as the leakage inductance of this transformer, and this is the magnetizing inductance of the transformer. Okay, this is the final structure of LLC converter. But you need to take a look at the structure of this. Okay, in previous lecture we said that if there is a parallel structure like this, then voltage here is sinusoidal voltage. Then the sinusoidal voltage should combine with inductive filter to be a current source here, right? So this is not comparable, will cause a problem. But I thought about this long time ago when I was studying this for the first time. Okay, thing is, actually there is an inductance here. Originally, the leakage inductance of secondary winding was here, but we moved artificially with some approximations. So we should consider there is a path, inductor path, Okay? You are not seeing this. There is an invisible inductor here, right? Then this becomes what? This current, sinusoidal current is coming out from the tank, and you have capacitive filter which works as voltage source. So comparability is okay. So comparability is met. This, I don't know this direction. So comparability is okay. Okay. So all the people, they are using this diagram without mentioning this feature, right? But this is the story behind of the structure. Okay. And I simulated this with PSIM. This is LK, LM, and this is resonant capacitor, which works as the DC block capacitor as well. And this is what? This is a capacitor filter, works as a voltage source, and somehow current is coming out this path. Okay. So this circuit diagram, this is a PSIM circuit model. Okay, everything is just normal. This is VCO. I introduced previous lecture, maybe 2 lectures ago. This one is, it works good. It is okay. This is okay. Okay. Maybe the VCO gain is non-linear. It's not linear. Okay. So it has non-linear VCO gain, but it really doesn't matter. And I just specified this is leakage inductance of this transformer, and this is magnetizing inductance of this transformer. I put small r here, maybe parasitic resistance. I remember without this, maybe there is some problem, simulation problem, because of the comparability problem. So we need to put something very small, okay, maybe inductor or like a small resistance, then this one works fine. Okay? This is the operation below resonant frequency. So VT, tank voltage, is this one, is tank current. So tank current, actually it starts somewhere here. So tank current is earlier than tank voltage. This is the GCS operation, and every waveform matches with our predictions of GCS operation of series resonant tank. Basically the same waveform. So this circuit is series resonant tank. There is a parallel branch of this L, but still it is a series resonant converter. Okay, and if you see there is something here, this comes from the DCM operation. We are assuming CCM operation all the time, particularly for the next coming analysis. We assume everything is sub-ideal, but in reality, there is a DCM operation here. So DCM operation is showing up here. And this is the IT1, I2, IT2, they alternate each other to create this IN, right? And this is the operation below the resonant frequency. And this operation has some problem. turn on with high voltage and reverse recovery from of slow body diode. Okay, this is the operation at resonant frequency. So you have exact synchronization in phase, everything. Okay, these are ideal waveforms, but you cannot get this. You cannot put your switching frequency at exact resonant frequency for 2 reasons. I explained that earlier. And next one is operation above the resonant frequency. This is the desired operation. So watch this. This is tank waveform, tank voltage, and this tank current. Tank current start here. So this is what? This is behind the voltage. So we have phase lag, phase delay, which is desired. And with this, above resonant frequency. Okay, let me go this one. So if you draw one vertical line here, this in this period D1 is conducting, and after this Q1 channel is conducting. So you have GBS condition here, right? And this waveform, we don't have any discontinuity. So this is a CCM operation, and waveforms are very similar to the sinusoidal wave. Not perfect, but very similar to the sinusoidal wave. So this is the desired operation. Okay, open no simulation. Maybe later homework, you need to simulate this. Then maybe you can use this. Or you can use your own. Okay, it really doesn't matter. All right. Let's talk about the dynamics and the control of this LLC converter. So this is a voltage mode control. We sense our voltage of this output and pass through this compensation circuit, which is actually a 3-pole 2-0 compensation circuit. And we are just using only output voltage as a feedback signal. So this is voltage mode control, and the signal is going through the VCO, and some logics provide a complementary driven 2-switch drive signals. Right. Okay, but this is not common one. Okay, because most people they design in the past they design the compensation controller of this type of converter arbitrarily. They selected arbitrary combination of this or something strange, and they have only integrated structure, then our voltage will be regulated, right? But the other performance will be suffered a lot. That was the way of they were doing at least 10 years ago. So my student, one of my students, he was working in LG Electronics, and he came to me as a student, and his topic was this one, dynamic analysis and control of this LLC converter. That was a very challenging task. At that time, nobody provided a systematic explanation about these things. Okay, we'll cover that later on. So with this is the optimal compensation structure. Okay, so with that, we have this. Okay, so this is the voltage feedback compensation for voltage mode control. 3-pole 2-0 structure, same as the PWM converter case. I put this to limit the out voltage. Okay, so this will protect some the malfunction of this in case. It won't allow to saturate this operation amplifier, so something was necessary. Okay, and this is the VCO I explained, and this is closed control. The VCO is working okay, right? At least for this simulation. And with this, I did step transient response simulation at low line. Low line means the input voltage was low. This was the practical application for the planar LCD TV, and the range of the input voltage is huge. In front of that, they have the PF circuit, and with some consideration of some disturbance in the line. Okay, grid is some sag or something. So the range was 200 something. Is bottom value, top value 3/8, very similar to the 400 volt. So this variation, input variation is very large. So we tested this performance of this design at low line. So this is the change in the load current is a huge change. 6 amp to this might be 1 amp. Okay, almost from the full load to low load, and it generates this response in the out voltage, and it shows the transient response of tank current. This is almost the optimal. It's very extremely difficult to get this response without this systematic analysis and theoretical control design. Okay, so this was okay. So we published this one for one paper, but this has some problem. This voltage mode control has some problem. Okay, this one is excellent in the low line condition. Okay, but if the input voltage is increased to go high line case, then transient response is less than optimal. Okay, compared to this, you may think this one is also good, right? But this magnitude is increased, and there are some disturbance, and response time is increased. Okay, this is the problem of voltage mode control applied to the LLC converter. Maybe you remember in the PWM converters, you need to use current mode control for the boost type, or all the converters other than buck converter with some problem. Same problem as here, but nature of problem is different. Okay, so we developed current mode control, and with current mode control, we obtained very similar response to the previous case, even with this very hard condition, hard operational condition. Maybe I don't have simulation result here, but later on I'll show that maybe something similar to this, and this goes like this. All right? Okay. But so this is the problem with voltage mode control and with current mode control. You can improve this much, and we obtained the performance consistent in all operational period. There are a huge change. This is the load change. Okay, load change is this much, and input voltage change is further wide. For the case. Okay, let me explain why this thing happens in all the resonant converters. Later on, you will notice the DC voltage gain of DC LLC converter looks like this. Voltage gain of this converter is, I try to be accurate here, and maybe something like this. Okay, so this one has two resonant frequencies. One is this, it's coming here, and another resonance is here. Okay, when R is very small, okay, very light load condition, something like this. Okay, this is resonant frequency. At this frequency is create a difference between L and LK, liquid inductance, and C. Right? There is another resonance, and here this frequency is coming combination of LK and LM combined with C, resonant capacitor. So there are two resonant frequencies. So dynamics of this is very complicated. Okay, if R is very small, this load resistance is very small, you are somewhere here. If R is large, you are somewhere here. All right. So if you are in high line, you are in low line. Okay, the input voltage is low one, then you need large voltage gain, DC voltage gain, to have constant out voltage. And if you are in high line, okay, input voltage is large, then to have the same output voltage, this gain should be reduced. Then you are increasing the switch. So this is high, no. This is low line. This is high line case, somewhere here. Then switching frequency for the low line should locate here, and for the high line, switching frequency should locate here to get the output voltage regulated. That means there are a huge variation in switching frequency. This creates a lot of problem in the past. Okay, we solved this problem with new current mode control, and problem with voltage mode control is slope of this curve. Slope of this curve is very steep here, and this here is slope is very gradual. Slope translates to the gain of some transfer function. So this is high gain and this low gain. So at this operational point, we designed the controller using this high gain, and if we move to this low gain area, performance will be suffered a lot. Okay, previously seen that. Okay, that design was the best design for the given condition. If you take another approach, you design your controller here, and you move to this place, you climb up to this operational point, converter becomes unstable. Definitely, it becomes unstable. All right. So that is the problem of voltage mode control. That was the problem the industry was suffering from. Okay. So we solved this problem. And we proposed current mode control. Nobody was using current mode control at that time. They were using some current sensing for the protection, switch protection. And we published the paper, some not so good journal, okay? And we forgot about everything. So now they are using this. They are making the chip of current mode control for this resonant converter. All the resonance converter, they are using some type of current mode control, okay? In some modified manner. And actually they are using digital control all the time, but the current mode feature is embedded in that control, digital control scheme, okay? So this is the story about the current mode control and the voltage mode control. So I'm not very interested in previous analysis, GCS and the GBS business. That is so old, okay? So people were studying that kind of stuff maybe 50 years ago, right? So there are a lot of materials there, but you don't have to track all the details about that. Just knowing the basic principle and proceeding forward is more important, okay? If you stick with those things, you spend the rest of your time, your lifetime for that, okay? Okay, so we move to the next step, which is this one. Topic of title is sinusoidal approximation, and I'll explain this in detail later, okay? So I posted 3 references on this. So first one is paper. First one is paper from Bob Steigerwald. I think his ancestors are from Germany. Steigerwald, okay. He was with GE, General Electronics, okay, very famous company, and that was located at Schenectady. That is the name of a city in New York. So I visited there, and I met him several times there. And previously, I was communicating with this about this. I was doing some project with the GE. That is the developing LCC converter module for the military applications, not LLC. At that time, they think the LCC is the best structure, but later on, we found the LLC is the best. Okay, so now everybody is using LLC. Okay, so paper from Bob Steigerwald. The other one is book script. SC okay. Script, SCRIPT, from Bob, but different Bob Erickson. He is the author of the famous book, Fundamentals in Power Electronics, and he is a student of Dr. Middlebrook, who is considered as the father of power electronics. Okay, I have the script for the several chapters, but he didn't publish this book. I don't know why. Maybe he is still writing. Okay, to complete the entire story. So I have scripted until chapter 5. So I posted chapter 2 of this unpublished book. Okay. Another reference is I posted this morning. Book chapter 9 from Bob. Bob is the nickname of robot, right? Robot. Erickson, okay. fundamentals of power electronics. He published the first version of this 1990 or I don't know, something like that. And 5 years later, he published the second edition. And 15 years later, he published the third edition. So what I posted is the second edition. Okay. So if I have everything in PDF format. Okay. But if I post the newest one, I'll be in trouble. Okay. Legally. Copyright issue, but I think this old version is okay, so I posted. I think this is most popular textbook in power electronics and best book in power electronics, except just one book. You know what that book is? From me. Okay. When I was writing this book, I swear I have a book better than his book. Okay, so my book should be better than this. This one is also a book, and in chapter 19 something, there is something about this resonant power converter. So that material is very good, very good. Okay, other than this, don't pay attention to them for now, okay? So you will get lost with that. You will be confused a lot, okay? And the resonant circuit we will be talking about it just four kind. So first, this one, you have L here, C here, and R. Actually RE, okay? This is a series resonant tank. We discussed this. And the second one is this structure. Oh, no. L is coming here, C is here, and R is here. This one is what? Parallel loaded quasi-series resonant tank. Okay. Another one, popular in the past was this structure. L is coming here. And the C is here, C is here. This one is LCC, okay. Last one is the one just we talked. This is LCC, okay, no, LLC. It's confusing, LCC, LLC. All right, this is a series resonant tank. This parallel loaded. Maybe series resonant tank. Okay. In this topic, we'll be dealing with these two structures, but result can be easily extended to the other ones. And furthermore, the result can be extended to any structure of this resonant tank circuit. Okay, maybe you have something strange in between, okay? Then the same approach can be applied. So the thing we're going to discuss is this named as sinusoidal approximation. Okay, so we talk about what is the sinusoidal approximation, okay? First, we discuss sinusoidal approximation applied to the sinusoidal analysis of series resonant converter, okay? So we'll stretch out our discussions to the parallel loaded series resonant converters and the LLC converters and LCC converters or any other converters. Okay, we'll take our result. Okay, this is the concept of sinusoidal approximation. We have structure of this series resonant converter. So this is a DC input. And we have a DC output here, and in between, this is full bridge switch network. Okay, it will convert this DC voltage into this pulse waveforms. All right, but this circuit, this tank circuit, LLC, I said everything will be reflected as a single register to here. Then this resonant tank will respond only to the first fundamental component of this sinusoidal voltage. No, this is a pulse voltage. So it has fundamental sinusoidal component. And this tank is only react to this, right? So if that is true, okay, that can be true if Q of this resonant tank is very large and operational frequency is at the resonance or near the resonance. That must be the true, okay? Then this statement is true. If resonant converter operates near the resonant frequency, this resonant tank practically responds to only the fundamental component, which is this, okay? This is the Fourier series, first component of Fourier series. Vt1 is magnitude of fundamental component, okay? Then these current waveforms are sinusoidal. And you have these square waveforms, but circuit is only responding to this fundamental component. So we can consider this as a sinusoidal input in our mind. Okay, you are not seeing this, but circuit takes as only the fundamental component. And with this structure, this current rectification, this is the voltage source. Output voltage appearing here is what? The square wave. Same shape of square wave. So we consider only fundamental component of this. Then every waveform of our interest in this tank region is sinusoidal wave of at the fundamental frequency. That means we can use this the simple AC analysis technique. Maybe you learned your school, high school, or sophomore or freshman in your university. Right? That easy story will go here, and we will analyze this tank circuit, and result of that simplified analysis will provide critical information of operation of this converter as a DC to DC converter. For example, the voltage gain of this converter input voltage to output voltage is same as magnitude of transfer function of this tank circuit. Evaluate at the operational switching frequency. Okay, it's so simple. Okay, we'll go through that soon in the next slide. The Steigerwald guy, he first proposed this in 1988. Okay, so they were using this technique. They know this one works, but nobody is documented in the paper format. So that was the number one reference I recommended. Okay, that is a very, very extremely important reference for this type of analysis. Okay. Okay, you did this. For example, this voltage gain, DC in, DC out voltage gain can be closely predicted with this analysis, and many other properties of this converter, like the GBS boundary or many other things, or the design procedure, tank circuit design procedure, all of those results are generated from this analysis. So this analysis is called sinusoidal analysis or sinusoidal approximation. So this is just the approximation. We are replacing this whole thing with this tank circuit excited at the resonant frequency. Just the approximation or analysis, and many people call it fundamental harmonic approximation or fundamental harmonic analysis. They are all the same things, and this is the technique they are using all the time. Later on, you will see this. This operation is very complex. This is a very limited region of CCM operation near the resonant frequency, above the resonant frequency. If you move the operational point away from that region, the operation of this converter is extremely difficult. Show some strange behavior, DCM operation, but you cannot study all of that. You cannot study in this manner. There are other techniques like state space analysis or some sophisticated analysis technique. Okay, with that, you can have some general picture, the waveform of this or behavior of this for entire frequency range for the entire operational condition. That topic won't be covered here. You are not interested in that. Okay, we don't need that. We assume this converter is at the desired frequency with the CCM, and we generate some result. and with design compensation and set up the design procedure for the tank and the compensation. That works for all the cases, even though we didn't analyze all the detailed operation of the converter, that will work. Okay? Very closely predicted manner. Okay? That is the thing here. That is the reason why we are focusing on this sinusoidal approximation and the sinusoidal analysis. For that analysis, you need to have some two basic things. One is the Fourier series expansion of these pulse waveforms. We went through that in the previous lecture. Another one is evaluating the average value of sinusoidal waveform. So rectify the sinusoidal waveform. Suppose this is the rectified sinusoidal voltage waveform. Then you evaluate this, average of this. Okay. Then this is magnitude of IT. Oh, sorry. Let me use this one. Magnitude of IT, and this is half the switching frequency, switching period. Switching period is TS here. So averaging is performed over the switching period TS. Averaging performed TS. Then result is very simple. You have this 2 divided pi, and this IT1, IT is the magnitude of this. Okay, so simple. Now suppose you have some phase delay here, this much. Okay, this phase delay is pi. So you have pi phase delay here. And peak value is, again, is IT. Then average value of this waveform. Evaluate over this switching period. For this case, we have, this is the rectified, right? So we have original, the sinusoidal wave was this, is this rectified. So you have this average value of this times this cosine of phase delay. This is very easy to figure out. Okay, you don't have to go through this. Just take this thing. Okay. Then this is the value. This is value. We will use this. Okay. So along with the previous result of Fourier series and this, you don't need any more Fourier series analysis or averaging process. This is all. Okay. Involved with this course. Okay. And this morning I prepared 2 additional lecture slides. We'll go through this. And this is the original lecture slide I intended to use. Okay. If you see the references, Erickson guy, he spent probably 20 pages to explain this. Okay. I find out a better way of explaining this. Okay. So we'll go through that. This one, according to the book, looks very complicated, difficult, and boring, tedious, but eventually it's very simple story. Very simple story. Okay, we'll go through that. I spent some time to figure this out. Okay. All right. Let's try to understand this. Okay. This is circuit diagram of series resonant converter. Don't pay attention to this. Just to forget about this. You are not seeing this. Okay, it's not here. Just to focus on this. This is the DC part of converter. This is the DC voltage, and this switch network is converting this DC to these pulse waveforms. So this part takes care of the DC, and this is also DC. This out voltage, VO, okay, and this out voltage is somehow connected with this by this diode rectifiers. Then voltage seen at this port is this scale waveforms. Same as this one. This switch network is transforming this DC voltage to this scale waveform. And we have constant voltage here because of the presence of this large capacitor. And this DC voltage is reflected to here as this one by function of this current rectifier. Okay? So this circuit is only responding to the first fundamental component of this because the characteristic of high Q, low pass filter, this one. So this is sinusoidal. this sign, the same current, IT, and the IR, gotta be same. Okay, let me use the notation of I1, because we are assuming the circuit is circuit responded only fundamental component, so current is just the fundamental component of switching waveforms. So I should use IT1. Okay. Previously I said we use IT and I1 interchangeably. Okay. So, all right. So this is actual waveforms. This is actual waveforms. But circuit is only responding this and this. So you forget about this. Consider this as the current waveforms and consider this as the voltage waveforms. Then all of these are what? AC network. Okay? Sinusoidal waveforms at the fundamental frequency of this switching frequency. All right? So this, in everything in here, you consider, we take this and take this, everything in here is just the AC circuit excited by the AC signal. So this is the first order harmonic model. Okay? So we are talking about this. We are talking about this. Model itself is approximation because we assumed everything in here is just the first harmonic frequency of everything. And this is DC, and this is DC, and this is the first order harmonic model or AC model or fundamental frequency model. They are connected through this connection. And next thing is we just specify connection between the magnitude of waveforms, which is shown here. Okay. Then that's it. That's all about this analysis. We already know this. This is the DC quantities. Vs is DC. And we are interested in this one. Magnitude of first fundamental component of this tank voltage. Then we went through this. Right? This is the Fourier series of this pulse waveform. This is the magnitude of fundamental component. We have relationship. So Vs DC is converted Vt1 of this much, this amount, as the AC waveforms. Okay. How about this? This is the AC current. This is the DC current. There is a relationship between this. Actually, this waveform is rectified and averaged. That becomes this waveform. We'll discuss this in the next slide. So the relationship between from here to there is just what? Just averaging. We went through in the previous lecture slide. So we know this magnitude of this current, then DC current is this one because of the averaged process. Okay? So we discussed connections here in terms of the magnitude of DC and the magnitude of AC waveforms. You have same operation here. Magnitude of DC here is VO, right? But somehow due to this Fourier series analysis, this VO is converted into this fundamental component, and that component is appearing this, okay? Actually, this voltage is this one, but if you only consider fundamental component, there is this. So we have this relationship among the magnitude, okay? And this is IR. IR is sinusoidal wave. So magnitude of this one converted to this. Because this is the current rectifier, this is the waveform, this is IR. IR is rectified version of this, okay, this one. And average value of this becomes load current, right? So there is a relationship between this IO and IR, right? They are same here. This relationship are exactly same, only the direction has been changed, okay? First, understand this, right? So obvious to understand, right? And second one is, last time I said the RE resistance seen through this port, output of the tank circuit becomes simply this number, magic number here, pi divided 8 divided pi squared, which translated 0.8. This is 0.8. 0.8 is coming here. Okay? Think about this, right? RE, we are just talking about the ratio between the fundamental component of VR and the IR. Okay? We don't have any interest other than that. Okay? Then IR, this fundamental component, this IR, magnitude of IR is shown here. That is related with IO through this equation. Which one is this? Okay. So relationship between IO and IR is coming here as this factor. So IO is here, right? And relationship between this out voltage and this VO, fundamental component of not VO, this VR1. This one is this one. From the Fourier series, we know this. Then ratio of this is 8 divided pi square. This is the magic number coming all the way through the analysis. And this number is coming, this simple functional relationship. Okay? So RE seen by this plot is simply RO, R times, this is the output resistance R. When this one is multiplied by this one, which is very close to 0.8, that becomes resistance seen by here. Right? Why we are doing this? Then we can separate this into 3 pieces. Right? Because it was connected through this. We know the every relationship, but it was connected through this, but we know the expression of RE in terms of this R. Then we can separate them. Okay? So next slide shows that concept. Overview of section overview number 2. So we have a DC model. Maybe the full bridge network is here. DC, VC goes into this as AC, fundamental frequency, AC, right? VT1. We know the relationship between magnitude, okay? And this is the tank circuit. So LC and RD is coming here, right? Seen at this port. So we brought the load resistance R to here with this scaled value of RE. Then we conceptually separate this. This is the DC representation, DC representation. This is the AC representation of fundamental frequency of that switching frequency. Then what you want to do is AC analysis. This is an extremely simple AC circuit, right? So this is what? Input impedance of this tank, seen by input port. This is the output impedance of tank, seen by this output. And one is transfer function from here to there is the voltage gain of AC signal from here to there. We call it H. This is GI, GO, H. Okay? Very easy to figure out. So every student, maybe the high school student, they can do this. Right? Very easy one. So it's good, okay? We can evaluate this, you can evaluate this, you can easily evaluate this, and most important is what is the implication of that result. How to make use of it is the problem. I'll show one simple example, extremely simple example. In this case, to evaluate, to find the voltage gain from DC in to DC out. So voltage gain from input, DC input to DC output, M. This one is M. And DC voltage gain, we want to evaluate this. Right? Then start from here. This is a DC, this is VS. It changed to AC. Magnitude of what? This one. This is AC. This is the magnitude of fundamental component of AC signal. Then this is transfer function from here to there. Extremely simple to evaluate. Then you have this. But for the evaluation of this, you should use RE, not R. Because R is reflected here. Right? So reflect here. Okay. Then you have this voltage, fundamental component of this voltage. Then you should reflect this voltage to the output. Okay. So you have Fourier series, but this role, previously, the Fourier series was this direction. Now Fourier series should be this direction. Then this will be flipped upside down. First it was 4 divided pi, and now this pi divided 4. If you multiply all this together, it becomes what? Magnitude of DC value. Okay? Okay, let me repeat. This is a DC. Once you multiply the DC with this 4 divided by, it becomes magnitude of AC. If you multiply this with this, then this is the magnitude of AC at this port. If you multiply this with this, there is the magnitude of what? DC at this output port. Okay? So you cancel this. Cancel this, that means the DC gain of input to output voltage is just the same as the transfer function gain of this tank circuit, fundamental frequency approximation circuit, evaluate at the switching frequency. Okay? So there is the result using all the people all the time for the analysis of this resonant converter circuit. This is the example. This is not example, this exact one. So if you evaluate the transfer function from here to there using the simple AC analysis, it looks like this. Okay? It shows something like this because this is a simple second order system. This is a peak value, and this peak value is characteristic impedance of tank circuit. You know this. You learn this. Okay? Then with Q, there is a peak. Right? So magnitude is this. This is a voltage gain from DC input to DC output. Maximum gain here is just 1. The peaking occurs here. Okay? Whatever peaking, how large peaking it may be, the peak value is always 1. Why is that? At the resonant frequency of this, they canceled. So you are not seeing this. Then the DC voltage is just appears here. You have just this R. This voltage is translate this. So voltage gain should be 1. Okay, that is the maximum possible voltage gain with this series resonant inverter. So we need a transform in between. With transformer turns ratio, you can increase the maximum voltage gain, whatever number you want. Okay, so without transformer, maximum gain is just 1. Right? If your switching frequency of this converter is at this resonant frequency, then gain is 1. If you move slightly above this, then you are somewhere here. If you go down this, then you are somewhere here. And this is the region of GCS. Okay, I'll explain this, why that is true. Okay, there is a close relationship between input impedance and this voltage gain curve. Actually, the input impedance is the mirror image of this. We'll show this. I'll show this analytically later soon. Very easy. There is some difference between this. This is GI, magnitude curve. They are mirror image. Okay. So in this region, with this decaying gain, you have this increasing input impedance slope. That means what? This area is what? GBS. Okay. With this increasing slope, this GI is decreasing. That means this is the GCS area. Okay. So you don't have to watch this. You just watch this voltage gain. If voltage gain is declining some region, then converter as in GBS operation. Otherwise, converter is in GCS operation. Okay. So that is the result. Erickson spent 20 pages to explain this. Okay? I did just 2 pages. Basically, same thing. Right? He's used some notations, something. Okay, so let me discuss the original waveforms. I intend to show this. Okay, this one is also good, but this one is better with preview of this. This one is much easier than previous one, much easier, but it's much easier to understand than previous 2 slides because you already have some idea about this approach. Okay, let me repeat this. So this is the tank. This is the switch network, and VS is converted to these pulse waveforms, right? And this fundamental component. So there will be some phase delay here because we are above the resonant frequency for the GCS switching. Okay, then you have some phase delay, maybe pi, right? That will appear here because it's the same current, and that will appear everywhere. Okay, So this is output waveforms. This is DC voltage appears here. And when these two diodes are connected, it's reflected here. All right? Because this should be in phase with this voltage and this, no, this voltage and this current should be in phase. Right? Because we just have R in between, then this phase delay appears here. Okay? So this is the actual waveforms, scale waveforms. This is the actual waveforms, sinusoidal waveforms of current, scale waveforms of voltage. We are just considering the fundamental component, and this is magnitude of fundamental component. Okay? Then this diagram can be translated into 3 parts, which are unnecessary. Okay? First, I tried to use this, but I found out this morning this whole thing is unnecessary because the previous lecture slide already they contain all of this information. Okay, but somehow I prepared this, and the Erickson he is paying very great attention to this. Okay, he put very value on this. So let's go back. Okay, so this is the model of this part. This is the current coming from this voltage source, IS. IS is, these two switches are connected. IS is the same as IT. And if two switches are connected, the other two are connected. And this IS is just inverted image of this one. So we have rectified waveform of IT1 here. Okay? So this is, IS is just rectified version of IT1 here, all right? And we know this, the average value of this is given by this expression from the averaging process I explained. And this phase angle is coming here, cosine phi, all right? So this is a relationship. So this is VS, this is DC current. I should use a capital letter here. IS is this one. Right? And this one is then this tank voltage. We just consider only fundamental component of this. This is the Fourier series expansion magnitude. So V1T is this one. And we have tank. We have but this RE, tank resistance is this one. Multiplied by something here. According to the previous analysis, you have this. And this output on R. R is here. And VO. And IO is going out. And IO is just average value of this I1, IR1, which is sinusoidal. Average of this is this one. We discussed this, okay, previous lecture slide. So you have this, okay. So you have 3 separate model and the dependent source model. Among this dependency of dependent source model is shown here. So with this, you can analyze everything, and we can analyze everything with the previous simplified circuit. Okay, the same thing. Right? So this is the result of this sinusoidal analysis. So I'll be using his model, Erickson, because he is some famous guy. So I should I should show some respect to him. So I'm using his model. Okay. Model is stupid, but still I'm using it. So there's a comparison between the original circuit model and this is the model developed by Erickson. And this is switch network and tank circuit and current rectifier and the capacitive filter. With this somehow there's a DC model, and in the middle we have, I don't know, where should be the borderline? Maybe somewhere here, that this one is tank circuit, and this is output circuit, okay? This looks like current source, it's not a current, this one is a voltage source. Our voltage should appear here, okay? So this is voltage source, right? And we have all the relationship between this dependency, between the dependent sources, IS and the VT1, and the VR1, and IO, and everything. And this is transfer function of input to output transfer function of this one. So this is simply this one, SL plus 1 over SC plus RE in downstairs and the RE alone in upstairs. Okay, so This is the equation. The same model, okay? So this is the transfer function of this model, input-output transfer function, transfer gain, denoted as HS is coming here. This is a transfer function here, okay? Relationship between VS and VT, VT1 and IT1, and VR1, IR1, IR1 and VO, okay? Actually, this is unnecessary, but she used that, so I copied from his book. So this is the first one, second one, and you know the ratio of this. 4 divided pi is coming here. This is the transfer gain of this resonant tank circuit. Evaluate at the switching frequency, and this ratio is just RE. This one is current, one is voltage. So ratio is 1 over RE, and we have factor of this coming from the averaging process. And R is here. So if you multiply this out, then what you get is simply this one. For this one is coming in the numerator, and okay, then everything cancels. This one, this one, this one. All of them cancels, and this becomes, no, not this one, I'm sorry. Oh, no. This is, I confused. Okay, forget about this. Just use the expression of the RE. RE was, I don't remember. 8 divided by pi square, then everything cancels. It cancels, and what you have is just HS, magnitude of transfer gain from the input to output of tank circuit, evaluate at the switching frequency, J omega S is the voltage gain of this whole circuit. Okay? It's exactly same as the previous analysis using the simplified circuit diagram. Otherwise, I'm lying to you. Okay? This gotta be true. Actually, we don't need this intermediate step at all here. Okay? Anyway, we derived the same conclusion in 2 different ways, but 2 ways are virtually the same approach. Okay? The conclusion of this is the DC conversion ratio, which is out voltage divided by input voltage in DC. Is the same as the magnitude of resonant tank function, resonant tank. Something is missing. Resonant tank transfer function evaluate at the switching frequency in terms of its notation. That was HS, magnitude evaluate at switching frequency. Okay, this is the result of this analysis, DC gain analysis, and this is very general, right? Actually, it does not matter the structure of this resonant tank circuit. Okay, for the parallel resonant, the parallel loaded resonant tank circuit, you have L and C in parallel with this. Just you replace this tank circuit there, then you will get the same result. Suppose you have LLC, just replace this with LLC, then you will get same result. LCC, same result. Some strange false order resonant tank circuit, just replace that circuit here and perform this AC analysis. If that one is complicated, just ask PSpice or something else, some stupid software to do job for you. Will generate nice plot. Okay, so this is extremely general conclusion. It goes for every series resonant converter. Okay, all the converter you will be dealing with in your lifetime. Right? What is the consequence of this? Suppose this is the example of LLC converter. So this is the plot of this one. We went through this, right? So in this region, this slope is decreasing, then input impedance will be something like this. You can prove, I'll prove this, okay? Then this is what? GBS region. This is the GCS region. Slope is very steep. Then gain, transfer gain, magnitude of transfer gain will be very large, will be small. At this point, slope is 0, then transfer gain will be 0, okay? So at this point, actually the control, in terms of control, the feedback gain becomes 0 because of the slope at this peak is 0. We'll go through this in great detail. Later part of this semester, which deals with dynamics and control of this LLC converter. Okay, so let's finish up the remaining slide very fast because you know the whole story about this. So just to evaluate this resonant tank transfer function at the switching frequency. Which one is this? Very extremely simple. Second order system. Then translate this using the standard notation. This omega naught is the resonant frequency of tank circuit. This is the quality factor. Okay, given by this ratio of this L divided by C inside of this square root is what characteristic impedance, right? Previously, we used the notation of the GO like this, but sometimes we use RO, same thing. Okay, dimension is just the impedance, so we call it characteristic impedance. And you put J omega here, and evaluate this and get the magnitude of that function. HS evaluate at J omega S becomes this one, this coordinate equation. Okay, so magnitude of this. Okay, put J omega here and get the real part, then imaginary part, and square each of them and put them in the 1 over square something. Then you will have this. Okay, this is the magnitude relationship, and this F is ratio between switching frequency and resonant frequency. Omega naught, no. F naught is just this one. Resonant frequency in Hertz. Fs is just the switching frequency in Hertz. Right? So this is the final equation. Okay? Put one here. That means switching frequency is the same as resonant frequency. Then this term becomes 0. Gain is 1. You went through this. Right? Otherwise, or you put J omega here, then everything will cancel. It will just becomes 1. That is the stupid way of understanding this. Just watch this. At the resonant frequency, they cancel. Then this voltage are the same as this. Obviously, voltage gain at the resonant frequency is the 1. That is the maximum gain you can achieve with this series resonant converter. And I plot that. Just to copy this. Okay, and that means if you evaluate this transfer function at this resonant frequency, everything cancels and just it becomes 1. So magnitude is 0 dB, 1. Okay, and in terms of a circuit analysis, L circuit behaves as a short circuit at the resonant frequency. Then those magnitude of output voltage gotta be same as magnitude of input voltage. Okay, otherwise some miracle happened. All right, that is the Borel-Pudor diagram of transfer gain, which is DC gain of input to output. So at this frequency, you have the, if you put your switching frequency at this point, somehow, then you will get the maximum gain of 1. Input and output voltage will be the same. Okay? Then you need to go through this. Then gain will be reduced. This is in dB scale. This is in linear scale. Right? How accurate this one is? How accurate this approximation is shown here. I got this curve from Erickson's manuscript, okay, unpublished book, manuscript of unpublished book, and he provided this. There are two curves. Okay, this one means this is the resonant frequency. Okay, when switching frequency occurs at this resonant frequency, you have maximum gain of 1. Okay, we move this direction means we are above the we are operating above the resonant frequency. Then this gain is decreasing. I think this is linear scale. So this scale one is exact. The other one is prediction. This scale one is prediction, and this white scale one is exact. There is a way of exact gain for all cases, but that requires extensive analysis. He has that result. He used that result, okay, and he compared the exact one and this approximate gain based on this sinusoidal approximation and the simulation result. So he compared that. So this accuracy is fairly good, this region, with high Q. Okay? So high Q is necessary to obtain the accuracy of prediction of sinusoidal analysis, and the larger Q, high Q, and closer the switching frequency, then accuracy is getting better. Okay? That is obvious. Because you are far away from the resonant frequency, the error will be increased. And you have small Q, okay, small Q, then this will be reduced, accuracy will be reduced. So the larger the QE and closer to the F4, the more accurate the prediction. Right? Okay, and I have one final comment. So this one is okay. No. This one is good. Very good. Okay, this one is okay. This one is entirely different. Okay, so analytically, theoretically, the prediction is this. This is the result of the exact prediction or result of the simulation. All the gain here, this part is just one. Okay, this is the result of the some different operational mode. In this region, with this below the resonant frequency, with very low Q, converter moves in entirely different operational region. It shows some DCM behavior, discontinuous conduction mode. Okay, and the voltage gain actually looks like something strange, like this. So it has huge error. This is entirely garbage here, but that is the limitation of this sinusoidal approximation here. Okay? Because we assume everything is sinusoidal, then might be true in this region, and reasonably true in this region is entirely false, just right in this region. Okay? So you should know the exact result, some case, but you will be playing in this area, so you don't have to worry about this. Okay? By design, you will have high Q, and by operation, you will have operation near the resonant frequency, then this accuracy is guaranteed. Okay? You don't have to worry about that. But if some strange operational mode, your converter will move this, then those strange waveform will come up, but that is still okay. That maybe sometimes that induce huge surge in the voltage or current will destroy your switches. Okay. Other than that, if everything is ideal, everything is fine. At least in the simulation. Okay. Just one additional comment. When I went Virginia Tech to study, they were studying all their studying is the operation in this region. They use space state analysis, phase plane analysis to predict behavior in this region. Okay, and they found out something very, very critical one, but nobody is paying attention on that now. Okay, because we already know the phenomena due to their work, and we know this thing can happen, so we should limit our operational region somewhere here. Don't go beyond this outside. Okay? Initially, one guy, Indian guy, his name is Lamish or some stupid name. He was doing simulation, and every time he is reporting some huge column spike. And Freddy, Dr. Lee, he was my boss. He got mad. Okay, you stupid. And he did some state plane analysis, and he identified that mode can really happen, and that will destroy everything if that happens. Then he found out the way of not entering that mode. That is the result of the previous research. But now everything is known, so you are safe. Okay, you don't go that tragic mode of operation, right? Okay, sorry for spending some time, but I want to finish up this part. Okay, so we move fast, right? Because there are a lot of things to be covered other than GCS, GBS, that small stories. There are small stories. This one is also very small stories. We should move forward, right? Thank you.